Aldol condensation, which is an aldol addition followed by dehydration. The purpose of this experiment is to carry out the double-cross aldol condensation between an unknown aldehyde and an unknown ketone, obtain the melting point and proton NMR spectrum for the product, deduce the structure of the aldol dehydration product and the starting materials by evaluating the data. Equation and mechanism. In the presence of a strong base, such as sodium hydroxide, aldehydes or ketones or mixed combination that have alpha hydrogens will react to form beta hydroxyaldehyde or ketone. If two different aldehydes or ketones are used, the reaction is referred as cross-aldol. When cross-aldol product is desired, the condition of the reaction and the type of the aldehyde or ketones has to be carefully chosen to maximize the percent yield by minimizing the possibility of different permutations of these reactants. For example, only one of the reactants could have an acidic alpha hydrogen. The beta hydroxyaldehyde or ketone product will spontaneously or non-spontaneously dehydrate to give alpha beta unsaturated aldehyde or a ketone. The mechanism of this reaction involves the following steps. Aldol addition product. Base catalyzed abstraction of an alpha hydrogen to form the enolate, the negative charge on the oxygen or the negative charge on the carbon. The enolate acts as a nucleophile and attacks the carbonyl of the other molecule to form the tetrahedral intermediate, and after protonation gives the beta hydroxyaldehyde. Aldol dehydration product. Abstraction of the alpha hydrogen formed resonantly stabilized enolate, the negative charge on the alpha carbon or the negative charge on the O as shown here. The OH leaves assisted by the formation of alpha beta unsaturated aldehyde, which is a conjugated system. Even though base catalyzed dehydration of normal alcohols is not catalyzed by a base, the dehydration of beta hydroxyaldehyde in the presence of catalytic amount of strong base can occur due to the stability of the conjugated enolate formed after deprotonation of the alpha proton. Procedure. Below are shown the structures of ketones and aldehydes that are going to be used in this week's experiment. Notice that the 4 aldehydes have no alpha hydrogens and the 4 ketones are symmetrical and have alpha hydrogens on both sides of the carbonyls. Under this condensation, double addition and spontaneous dehydration occurs, giving colored yellow to orange solid products that have extended conjugation. The solid products will be purified by recrystallization. In this experiment, you'll have to determine if a single or mixed solvent needs to be used for recrystallizing a particular product, and if a mixed product is used, what ratio of the mixed product is needed. Data analysis. You'll be assigned one of the above 4 ketones, and you'll be assigned one of the 4 aldehydes as an unknown. Your mission is to identify the unknown aldehyde you are assigned based on melting point and the proton NMR data product. The melting points of the 16 possible products from 4 possible ketones and 4 possible aldehydes are shown below. 2 hints to help with interpretation of the proton NMR. Beta protons of a conjugated alpha-beta unsaturated ketones are more strongly deshielded than the alpha protons. Chemical shift of axial proton is greater than equatorial by about 0.5 ppm if a ketone containing a cyclohexanol is used.